Okay, good afternoon. We'll pick up again where we stopped, which was diodes, introduction to diodes and diode circuits. So today we'll look at a few analysis techniques. And let's see, large applications of diodes, large signal applications, share. Okay, so large signal applications of diodes. First thing is, what do we mean by large signal? Okay, so there are analysis techniques devoted to different diode models. Broadly classified, we can say them large signal and small signal. Large signal in this case would be something that is sufficient enough to turn on a diode. Okay, but typically we refer to large signals with like DC, but doesn't necessarily mean that it's only DC. We can apply like a 10-volt AC signal to a diode that could also be considered as large signal. Okay, so in general, large signal would be sufficient enough to turn the diode on and put it in forward bias mode. So one of the most common applications for a diode is in rectifier circuits, where we convert AC to DC. It's the most common circuit or application for a diode. It's present in every single electronic device that has a that can connect to an AC outlet. So your laptop chargers, adapters, monitors, projectors, cameras, everything that is powered from a wall outlet from AC is always converted into DC. So there's a power supply that is built into all of these electronic devices. Inside this monitor, inside the computer, the monitors that are on the wall, everything has a rectifier circuit inside it. And the diode rectifier circuit forms the most basic, most fundamental, and the first step in rectification from AC to DC. The simple reason is because diode is a one-way device. So when you apply a AC signal that pulsates from positive and negative values, it'll only conduct in the direction that it's configured. So if the anode is connected to the power source, positive of the power source, it will conduct in the positive cycle. If the cathode is connected, then it will be the negative half cycle. Later on in this chapter, we look at the diode rectifier circuits. We will look at those on Monday next week. On Friday, I'm going to cover the BJT transistors, because next week's labs are CE amplifiers based on BJTs, bipolar junction transistors. So we'll cover diode analysis techniques today, sufficient enough to get you started on the homework. There's a homework posted. If you haven't taken a look, please take a look. I'm going to cover the analysis techniques today. And then Friday will be the offline, not offline, but non-proctored quiz that you can take at your own time. And I'll post the announcement later on today. Yes. Homework is, let's see, what due date have I put? 18th is, why is it not coming up? Friday. Friday? No. So it should be either Saturday or Sunday. So, yeah. All right. The other one of the other applications is we can create digital logic gates using diodes. But again, those are very basic and rudimentary. They are not, you would not use it for any sophisticated application. And then DC restorer voltage multiplier circuits, we looked at that in lab 1. So a combination of the peak detector and the negative clamper results in a voltage multiplier circuit. And there are other wave shaping circuits that we can use the diode. Wave shaping is so-called because depending on the configuration, depending on the circuit schematic, it changes the AC input signal that's coming into the diode circuit. Okay, so diode equation. This is the fundamental equation that describes the relationship between a diode voltage and diode current. This is also known as the Shockley equation. Okay, named after William Shockley. He was one of the 3 co-inventors of the bipolar junction transistor. That's the first solid-state device that was displayed in the world. Okay, so let's break this down. This is diode current. This is diode voltage. Then we have IS, which is saturation current. This is a function of the design and doping. So it's in the hands of the manufacturer, and manufacturer specifies this on the data sheet. So it's manufacturer provided. The manufacturer provides this value for saturation current. And then we have E raised to VD over NVT minus 1. VT is the thermal voltage. We spoke about this. It's KT over Q. K is the Boltzmann's constant. T is the temperature in Kelvin, and Q is 1 unit charge. For most purposes, we use room temperature as 300 Kelvin. Just a nice round number. It's 25.8 millivolts at 300 Kelvin. 300 Kelvin is 27 degrees C. 27 degrees C Celsius is 27 times 2, 54, 54 plus 32 is about 86. So it's 85, 86 Fahrenheit. So obviously the temperature in this room is not 85, 86. It's probably closer to 72. So 72 would be 72 minus 32, 40, 40 approximately half, about 19 or 20 degrees C. So the temperature in this room is around 19 or 20. Add that to 273 Kelvin, comes out to about 293 Kelvin. So if you're performing a quick calculation, you can use 25.8 theoretical calculations. But if you're an engineer working in the industry, obviously you cannot just take a shortcut. You need to know the operating temperature for your circuit. And then from that, you will calculate the rest of your design. Okay. So the T in this room, the temperature in this room, probably around 292 or 293 Kelvin. Anyway, so that's thermal voltage, also known as the Einstein's relationship. Then we have, let's see, emission coefficient. That describes the non-ideality factor of the diode. Typically, the value ranges between 1 and 2. Most diodes, it's always 1. So if it's not given and you're performing an analysis, you can simply take it as 1. So typical values, always 1. Okay, so that's the diode equation. So if we take this exponent, it would be large enough, excuse me, large enough that we can ignore this 1. Okay. Again, this is for an approximation. So the equation can reduce ID is equal to IS into E is to VD over VT. Okay. So IS into VD over VT. So it's a function of temperature and a function of design. Okay. So far, so good. So if we have the diode voltage, we can calculate the diode current. If we have the diode current, we can calculate the voltage by taking IS on the other side. Natural log, and then times VT. Okay, so given the voltage, we can find current. Given the current, we can find the voltage. All right. Any questions? Question being asked, is n equal to 1? Yes. That looks more like a 2. 1. It's measuring it's describing the non-linearity of the diode device. That's again specified by the manufacturer. So this would also be manufacturer specified or provided. They would provide this on the data sheet. IS and N. Typically, if it's not provided, we simply assume 1. Even if it is higher than 1, it would be like 1.1 or 1.2. So unless you're sitting there and designing a circuit for like a mission critical, application where you absolutely need all the values, other than that, you can safely assume it to be 1. Okay, so that's the equation. Now let's look at some diode models. Okay, so there are a few different models. This is one of the large signal models that we can use for quick and easy analysis. This is I use these models every time I have a diode circuit. Okay, it's very quick and easy to analyze circuit using, not easy, but straightforward, using the ideal diode model. So the ideal diode model simply assumes that the diode does not require 0.7 volts to turn on. As long as the applied voltage is greater than 0, the diode turns on. It's in forward bias. There is no specified value of the diode voltage, meaning if you apply 5 volts to the diode, it's going to turn on and be operating in forward bias. If you apply 0.1 volts, it's going to turn on. If you apply 0.000001 volt, it will still turn on because it's greater than 0. Again, it's an ideal diode model. Okay, so nothing to do with obtaining actual values. Though even the analysis with this, when I teach the EE class, we analyze the same circuit using 4 different kinds of models, and we obtain values that are actually very similar. So even the ideal diode model gives us values that are actually useful. Okay. All right. So the ideal diode model, if you apply a voltage to the diode and the diode voltage is positive, greater than 0, diode is on, it's in forward bias, we represent it with a short circuit. So short circuit. If the diode voltage VD is less than 0, meaning it's negative, diode is reverse bias. So this is reverse bias, this is forward bias. And if the diode is reverse bias, we say it's off. And when it's off, it behaves like an open circuit. So we replace it with an open circuit. This is assuming, of course, that it's not going to break down. But all of that is ignored, right? All of that is ignored. So diode in forward bias is on, replaced with a short circuit. Diode in reverse bias is off, replaced with an open circuit. This is particularly useful when you're analyzing circuit, trying to understand the operation of a circuit. For instance, think back to lab 1. Lab 1, we had the 555 timer chip operating as a stable multivibrator and an oscillator. So its output is a rectangular, a square wave. It's on, then it's off, it's on, then it's off, right? Then we feed this output into a diode circuit through a capacitor. So capacitor, when the diode anode is positive, meaning the output of the 555 is positive, diode turns on, capacitor charges. When it turns negative, the diode turns off. If it's off, there is no pathway for the capacitor to discharge, so it holds the charge steady across itself. Then we added another circuit, another diode circuit, operating principle is still the same. But now it was connected in the opposite direction. It doesn't matter whether it's connected opposite or not. It's opposite direction simply because we wanted negative operation. So cathode was connected. When the output voltage goes negative, diode turns on, capacitor is able to charge. When the output goes positive, diode is off, circuit gets cut off, capacitor has no place or no pathway to discharge. So that's a quick and straightforward way to analyze using the ideal diode model. Okay, so even while explaining things in the lab, it's very useful. Right? Does that make sense? Diode voltage positive greater than 0, then diode is on, replaced with a short circuit. If it's less than 0, if it's negative, it's reverse bias, it's off, replaced with an open circuit. Yes. Well, it'll be 0 volts across the diode. It'll be 0 volts. So a question being asked is the voltage across the diode, would that be constant? Well, the voltage across the diode would be 0 volts because it's a short circuit. Okay. And then we'll look at a couple of examples later on, and then it'll make a little bit more sense. Okay. But obviously this is an ideal diode. Ideal components do not exist. So to get a better value of the voltage and current, we use a different model known as the offset diode model. The offset diode model is exactly the same as the ideal diode model in reverse bias. The offset diode in reverse bias is exactly the same. Diode is off when it's reverse bias, and when it's forward bias, diode is on. But the offset diode takes into account that it takes about 0.6 to 0.7 volts to turn it on. And once it turns on, it's going to hold that voltage constant across its terminals. And because it holds the voltage constant, we can say that it behaves like a voltage source, and the value is 0.6 volts. I stick with 0.6 because the book uses 0.6. If you're an engineer, you're working with a silicon diode, you could use 0.7. If it's a Schottky diode, 0.2, 0.3, germanium diode, either 0.2 or 0.3, right? But again, this accounts for the voltage that is required to turn on the diode. So reverse bias, it's off, open circuit. In forward bias, it behaves like a short circuit in series with a voltage source. So this would be the ideal diode model in series with the voltage source, 0.6 volts. So offset diode model would look like this. Forward bias, it's a short circuit and a voltage source of plus 0.6 volts. Okay, this is of course forward bias, right? Forward bias. This is also known as the constant voltage drop model, or CVD model, because we are holding the voltage drop across the diode as a constant. Obviously, you perform the experiment, so you know the voltage is not a linear line. There's actually a slope, right? The resistance changes because there's a slope in there. So it's not quite just a straight line pointing up. So it's not just 0.6 volts. But again, it's a model that we use for analysis. And again, it's similar to the ideal diode model. It's a quick and straightforward way to analyze the circuits. Okay. By the way, CVD stands for a fabrication process. We use it in semiconductor fabrication, chemical engineering. CVD stands for chemical vapor deposition. This is the process that you use to grow diamonds in the lab. You pass gas into a vacuum chamber, typically like methane gas that contains carbon, at the right pressure and temperature, decomposes, carbon separates out, and it deposits onto your sample as a diamond film. That's chemical vapor deposition. So for me, I have to be kind of like careful depending on what class I'm teaching. CVD means something else. Okay, ideal diode model. Ideal diode model analysis using ideal diode model. Okay, first step in the analysis. So this is ideal diode model analysis. Right. We assume a diode state either on or off based on our observation and of course circuit conditions. Okay, circuit conditions, meaning there are sources connected into the circuit. So we'd like to we have to follow rules and certain logic, and we make assumptions. Okay, so if the anode is connected to a higher voltage level than the cathode, more likely than not, the diode is on. So we can assume a state for the diode as on. And then we analyze the circuit after we replace the diode with a short circuit or open circuit based on assumptions. Okay. Anytime we replace a component, the circuit changes. When the circuit changes, your analysis would change. Okay. So always redraw the circuit, and we'll look at an example of that just in a few minutes. So when the circuit changes, your analysis should change, should not remain the same. Okay. At the end, we need to verify whether our solution is or assumption is correct or not. So the things that we need to look for are this. If it's on, VD would be 0. Okay, VD would be 0. But more importantly, it's a short circuit. So there's a pathway for the diode current to flow through. So diode current ID must be positive, must be greater than 0. Cannot be equal to 0. It must be greater than 0. It must have a positive value. If it does not have a positive value, that means that the diode, our assumption is incorrect. Okay. So far, so good. If we assume that the diode is off, that would mean that diode voltage is negative. So diode voltage must be less than 0 or negative, and diode current should be equal to 0. If it's a reverse bias, it's off. There's no current flowing through. Again, it's ideal diode. We are not looking at saturation current. We're not looking at values. We're not looking at anything. Okay. So let's take a pause while you write it down, think over it. Let me know if you have any questions. It's 2:35, so we got time. Any questions? Yeah. So the question being asked is, would these values hold even if it was offset? The answer is yes, because the offset model is exactly the same as the ideal diode model. So let's go back to there. And the model is simply going to be a short circuit in forward bias, and you have a 0.6 volts voltage source. So we'd analyze the circuit as it is and treat this as a voltage source of 0.6 volts. And then in reverse bias, of course, it's off. And so that's exactly the same. Yeah. Okay, so the question being asked is, why would the voltage be less than 0 in the off state? So in order for the diode to be off, it must be reverse bias. If it's reverse bias, meaning the diode voltage is is negative, which is less than 0. Diode voltage is always measured with the anode at positive, the positive at the anode and negative at the cathode. Okay. So greater than 0 would mean that anode is higher than the cathode. Less than 0 would simply mean anode is at a lower potential than the cathode, hence a negative diode voltage. And we'll see that in the example that we'll solve. Okay. Okay, so we perform our analysis, we check and verify whether our assumptions are correct or not. If our assumptions are not correct, we have to redo the analysis by choosing the other state. Okay. That is easy to do when you only have one diode in the circuit. Okay, because one diode equals only 2 possible states. So 2 possible analyses. If the first analysis is incorrect, you use the second one, right? However, the number of states is going to increase. It's like the binary number system. If you have n number of diodes, then, okay. Then possible states. How many possible states do we have? 2 raised to n. So if you have 2 diodes, you have 4 possible states. If you have 3 diodes in a circuit, it's 8 possible states. If it's 4 diodes, you have 16 possible states. Okay, 16 possible states. And the example that we'll look at actually has 2 diodes. Okay, so we'll look at that. But one important point is that, let's say you have 2 diodes. So there's 4 possible states. Either both diodes are on or both diodes are off, or one is on, the other one is off, or it's off and on. We'll make the assumption based on logic, and then we hope the first one is correct. But invariably, it would turn out to be incorrect. So let's say you assume at the beginning D1 on, D2 off. And you perform your analysis. It turns out D1 was correct, D2 was incorrect. So our next logical state would be D1 on and D2 also on, both of them on. Okay, but it is not always correct to assume that both diodes will be on. If you make an assumption of a diode circuit which has 2 or more diodes in it, if you make an assumption and it turns out to be incorrect, it does not mean that one of those diodes is correct and the other one is not. It means the entire assumption is incorrect. Okay, again, if you have 2 diodes in a circuit, D1 and D2, you assume D1 on, D2 off, and you perform your analysis. It turns out D1 assumption is correct, D2 is incorrect. So the next logical step you would think would be to make D2 also on. But it's not necessary that D1 on, D2 on will also prove to be correct. Not always true. You cannot just make one change. You have to you have to throw out the entire assumption. All right, so let's look at an example. We have a circuit that has 2 diodes, 2 voltage sources on either side, and we are tasked with using the ideal diode model to analyze this circuit. Okay. Now, just to observe the circuit, what do we see? We see that the anode of D1 is connected to the positive end of 10 volts. And we see the anode of D2 is connected to the positive end of 3 volts. So if both anodes are held at a positive level, the first thing that comes to mind is that both diodes are on, right? Both diodes are on. However, the 10-volt source is more than 3 times or 3 times more than the 3-volt source. So chances are that the midpoint right here is probably greater than 3 volts. This is just based on observation, no analysis, nothing. Just logic, intuition, observation. So if the cathode, the midpoint is greater than 3 volts, then the cathode of D2 is likely higher than the anode. And if that's the case, then the logical assumption to make would be that D1 is on and D2 is off. Okay, that's a logical assumption I would make if I was analyzing the circuit. But for explanation purposes, let's choose something that I know it's incorrect. So number of possible states, we have D1, we have D2. Both diodes are on, both are off, or D1 on, D2 off, and D1 off, and D2 on. This is circuit number B. No, this is circuit number C. And this is circuit number B. Okay, circuit number B. So D1 is off, D2 is on. Circuit has changed. If circuit has changed, I need to look at the circuit again and then analyze. Okay, so D1 is replaced with an open circuit, and D2 is replaced with a short circuit. Open circuit and short circuit right there. Okay, so let's look at D2 because that's the easiest to analyze. So D1 is open circuit, D2 is short circuit. The right side of the loop, the left side is completely disconnected because of the open circuit assumption, right? Completely disconnected. So the right side of the circuit, by applying simple Ohm's law, I can find ID2. It's a series circuit. Current just simply flows through the source and the resistance. And so I can find ID2 as 3 volts divided by 6,000. So 0.5 milliamps. Current ID2 is positive, and because it's positive, therefore D2 is on. At least one half of my assumption is correct. Okay. Let's take a pause while you write it down. Let me know if you have any questions. Now we need to find VD2. Sorry, VD1. VD1. Diode D1 is assumed to be off, so VD1 must be negative in order for the assumption to hold true. So it's a simpler circuit, so we can make direct observations. What is the voltage at the anode of D1? What is the voltage at the cathode of D1? Cathode is connected right here. This point is disconnected from everything except the 3-volt source. And so I can say it is 3 volts. So voltage at the cathode of D1 is 3 volts. Voltage at the anode can be found by considering the open circuit. So this is the fundamental principle. What is the current flowing through R1? Or the 4 kilo ohm resistor? Sorry. 0, right? Diode is open, so there's no pathway for the current to flow through. So current through the 4 kilo ohm resistor is 0. If current through the 4 kilo ohm resistor is 0, what is the voltage drop across the 4 kilo ohm resistor? That is also 0, right? If both ends of a resistor, I'm sorry, not both ends. The voltage across the resistor is 0. That means both ends of the resistor are at the exact same voltage potential. If they're same potential, one end is at 10 volts, so the other end is also 10 volts. And that's the principle behind it. So if you have a resistor connected to a voltage source and the other end is left open, it's not connected to anything, the voltage at that open end of the resistor is the exact same as the voltage at the other end. So voltage here is the same. Sorry, not there. Voltage here is the same as the voltage here. So it's 10 volts. Therefore, VD1 is equal to plus 7 volts, where VD1 has turned out to be positive. It needs to be negative for our assumption to hold true. And because it's positive, that means our assumption is incorrect. D1 is on. Assumption incorrect. Okay, assumption incorrect. Does that make sense? Now, every circuit is different, so the analysis is not the same. Analysis would be very different for every single circuit. Okay. This is just an explanation. So now that we know that this is incorrect, we have to change our assumption. There are three other possible states, three other possible combinations. We can choose any one of those three. If it turns out, if you're bad at picking the assumptions or observing the circuit, that means you're going to keep on doing until you get it right. So it doesn't mean that you're bad at it. It just means circuit sometimes gets complicated. Okay. So the next logical assumption would be that D1 is on and D2 is off. So that's what we choose for circuit number C. And now the exact same analysis applies on the left side of the circuit. So I'm going to do this here. We'll assume D1 to be on and D2 to be off. If D2 is off, replace with an open circuit. And D1 on is replaced with a short circuit. So the left side is disconnected from the circuit itself because, again, it's left open. So I'm going to work with ID1. ID1, because of the assumption made, because of the open circuit, now the 4 kilo ohm resistor and the 6 kilo ohm resistor are in series. Right? They are connected together at the top, and there is nothing else connected to that terminal. There's no other component connected to that terminal. So they are considered to be in series. Current has nowhere else to go except through both the resistors. So ID1 is equal to 10 volts divided by 10,000, which comes out to be 1 milliamp. It's positive. Therefore, D1 is on. Okay, D1 is on. VD2 in a similar manner. VD2 is the anode voltage minus the cathode voltage. And in this case, the anode voltage is 3 volts and the cathode voltage would be 6 volts. Because 1 milliamp is flowing through 4 kilo ohm and the 6 kilo ohm resistor. Voltage drop across both of them is 4 volts and 6 volts. So now the midpoint is at 6 volts. So diode voltage VD2 is minus 3 volts. Hence, D2 is off. And our assumption is correct. You could try, for practice, you can try analyzing the circuit for the other two states. You already know that it's going to be incorrect. So just do the quick analysis and see what you find and see what you get. It'll help you understand it better and then help you in solving the homework. Okay. It's already 2:52. We move on. Okay. So that was the ideal diode model. We have a couple of models for small signal analysis. In small signal analysis, what we do is we consider that we are applying a AC voltage that is small enough compared to the large signal DC bias. So it's small enough, it only shifts the diode characteristic a little bit up and down. Okay, so it's a very small movement. Because it's a small movement, we are only looking at a small piece of the diode response. And if it's a really small piece, we can consider it to be linear. And if we consider it to be linear, we can apply linear circuit analysis techniques to that small portion. One of the first ways to analyze a circuit is by load line analysis. Load line analysis is a graphical technique In a graphical technique, you have the plot of the diode characteristic. Okay, the diode characteristic can be described by the diode equation, ID and VD. Two unknowns in that equation. If you have two unknown variables, how many equations do we need to solve? We need two, right? We have one equation from the diode characteristic. We can treat this portion of the circuit as linear. That's like a Thevenin equivalent. Reduce everything to one single voltage and one single resistance. And we plot a linear line to account for that circuit. When we plot a linear line, you now have two plots. The intersection point of those two plots, which is right here, is known as the Q point. Q point stands for quiescent. Quiescent. Hope I spelled that correctly. The quiescent point in a circuit, the word quiescent means dormant or lying in wait or being prepared. In our case, in electronic circuits, what it means is we have applied a DC voltage, DC current to our circuit. So our circuit, whether it's diode or transistors, MOSFETs, is now lying in wait and is prepared to accept AC input signals. Hence the name Q point. Okay, so if anyone says Q point, more likely than not, they're referring to a DC applied voltage to a circuit. That DC voltage causes the diode operating point to be fixed, which is what we did in lab 3. Circuit number 1 was diode biasing. You're applying a DC voltage. When you apply a DC voltage, you have a fixed diode voltage and you have a fixed diode current. That point does not move. That point is fixed on the diode characteristics. Hence, it's fixed. Now, if you apply a small AC voltage or AC signal on top of this DC application, your Q point will either shift up or down the diode characteristic in response to that AC signal. And because if the AC signal is small enough, we can analyze that shift up and down. Okay, as long as only DC is applied, it is fixed. When you change the DC voltage, obviously diode voltage and diode current would change, but other than that, it remains fixed for a constant input voltage. Hence the name Q point. So the way we create this load line, this line is known as the load line, hence load line analysis. So the way we create this load line is by applying KVL to the circuit. When you apply KVL to the circuit, we can obtain Vs is equal to IDRS plus VD. It's a linear line. We need values for ID and VD to plot. So the assumption is the line is going to intersect the X and the Y axis at some point. So we choose if ID equal to 0, we can find VD as equal to Vs. And if VD voltage is equal to 0, we can find ID is equal to Vs over Rs. And those are the 2 points right here. Once you have those 2 points, you join it, you have the load line. The intersection of the load line and the diode characteristic is the solution to that circuit. So the value of the voltage and current at the Q point is the diode voltage and diode current when you apply its particular fixed voltage. Okay, because the line will shift depending on what your supply voltage is, right? If your supply voltage decreases, line is going to shift to the left and the current is going to shift down. It's still going to remain linear. And if Vs increases, it's going to move up. Okay, hence the load line analysis. I have just a few minutes left, so I'm going to go over to the next topic, which is piecewise linear analysis. So the piecewise linear model, we treat the diode as a linear device. Okay, linear device because we are treating it in this portion. After the diode turns on, we can consider this portion to be linear. If it's linear and has a slope, that means it can be modeled using a resistance, hence diode resistance. Okay, so this would be the diode characteristics. And we are plotting this as a linear line with a slope. And this is the load line from the previous explanation. And of course, the intersection point gives us the Q point. The intersection of the diode characteristic gives us the diode turn-on voltage. In this case, they call it V gamma, but that's the diode turn-on voltage. Okay, diode turn-on voltage. That's what it represents. And once it turns on, it's going to hold this constant. So it's going to be linear in this portion, right? So it's turned on, and it's turned on. It's going to hold the voltage constant. So we're going to say that it's about whatever the value is, 0.5, 0.6, 0.7 volts. And we're going to hold it as model it as a battery or a voltage source. And the rest of it, we can model as a series resistance RD. If you measure it at one single point, it is known as static resistance. And if you apply an AC signal on top of it and your load line shifts up and down, we can take 2 points that are on either side of the Q point, very close together. And if we do, now if you calculate delta VD or delta ID, change in the diode voltage and a corresponding change in the diode current, we get RD. Okay, that would be known as dynamic resistance because it's between 2 points. And slope of the line, Y over X, Y over X, slope of the line gives us 1 over RD. Okay. So again, if you take it at one single point, if you take it at the Q point or any other point, it's static resistance, simply voltage over current, applying Ohm's law. If you take any 2 points, you're measuring change in voltage and a change in current. So you get dynamic resistance. All right, so we're going to end class here today, and we'll pick up here again on Monday. On Tuesday, sorry, not Tuesday, on Friday, I'm going over bipolar junction transistors, BJTs, and their applications like a CE amplifier in preparation for Lab 3. Okay, so we'll come back to diodes after I introduce BJTs on Friday. All right.